So what I was saying was, all the morphs can be produced by just grinding. Yes, I asked this question. It's me. Yeah, I mean when you add in all these things, but how do you get single crystals? Exactly the same thing. I went to few labs. Whenever I went and started asking the same question, they say what you do in the case of either ball mill or pestle and mortar when you grind them, that generates a lot of heat. Okay, in the case of pestle and mortar, maybe a few hundred. You don't realize locally. And ball mill, maybe several. According to them, it's several, which I don't believe. But at least several hundreds when you do in ball milling, local in spots. But at that high temperature, people say that things can melt. Things can melt and then crystallize. But again, you are continuing grinding. When you continue to grind, you are smashing all the crystals. What is happening in this case, when you grind them and leave it, you usually add few drops of solvents. When you add few drops of solvent, this is the mechanism, okay? When you add solvent, when you grind them, the solvents, the reaction will happen in the solvent medium locally, even a drop. That's where the reaction proceeds, and the solvent goes to the next, mixture when you grind them, and then you get the product. That's how it's hopping. The solvent, a drop of solvent that is hopping, that is what is happening. The same thing when you grind without anything, that's neat. That's what they say. Without any solvent, the heat producer, sometimes it melts, the melting, the reaction occurs. So you get the product, no doubt about it. So after that, you just leave it, right? Those where you have those drops of solvents present, that will be used to crystallize. But not every crystal, single crystal, all the powder will be converted into single crystal. You see few single crystals based on how much solvent you added. Few, 3 or 4 single crystals you see, it started glittering, so reflect, due to reflection in the light, to shine. You can see the single crystals and you can remove it. I think that's the only reason I can explain, because when I talk to people who are all working on it, they said, yes, we do get single crystals. If you carefully look at it, few, 1 or 2 single crystals forming from the drop of solvents that you added. That's why the nature of solvent that you added, the liquid that you add, also has some effect on the product that is formed. Now, I hope that makes sense. Okay, these are the guys who have done a lot of work on this mechanochemistry. Now, this has been extended to all other areas too, and many of the organic synthesis can be done this way, just by mixing without solvent. And they want to prove that this is possible. That means in large production, if you can make it, that eliminates all these hazardous solvents, and then synthesis becomes easier. Okay. And we move on. All right. Now this slide shows that you can convert different forms, polymorphic modifications, just by grinding in different solvents. That's what I mentioned to you before, because solvent has influence. This is anthranilide. I think this is anthralinic acid. Anthralinic acid. It crystallizes in 3 polymers. It depends how you do that. You can interconvert them. The structure is shown here. Form 1, it has got both, the unionized one and zwitterionic. You see what I mean by zwitterionic? The proton is transferred. It is ammonium salt. This is an acid. Okay, that's zwitterionic ammonium. According to them, if you take it and you melt it, you can also melt and recrystallize, so you get only form 3. Neat means you just grind them. There's no change. And here form 2, again, if you grind them without any solvent, it doesn't change. Whereas here in astronitrile, it is present. But if you grind them neatly, it goes to 3. Form 1 goes to form 3. Like that, you can interconvert. If you add a drop of heptane and then you grind it, you can convert to one form to another. That's quite interesting. So you can use this solvent, while grinding, you can convert from one to another. In one case, if you add water, it goes from form 3 to form 1, and in chloroform 2 to 3, and so on and so forth. This is clearly mentioned here. I mean, then the question, how do they do it? By using powder, because they have the crystal structure already. Okay, they crystallize it and they determine crystal structure. But using the powder pattern, they can very easily do it. And in the case of co-crystals, that's what we are going to see later. Caffeine, glutaric acid, co-crystal. I mean, I have no other choice to introduce them in advance. Many times it's inevitable. So if you add this to, because this has got acid, this has got proton, and this is carbonyl, and so and also nitrogen, so proton acceptor. So it forms salt, and there are 2 forms available. Again, they say neat grinding or grinding in the presence of a non-polar solvent will get you one form, whereas kneading in the presence of polar solvent will get you form 2. So these things are available. So we do know now that solvent has a lot of influence on the form, crystallographic form. Okay, now when you talk about crystallization, basic crystallization, and we want to, it's not complete without talking about the work of Louis Pasteur, crystallization of chiral solids. And also, many of you are quite familiar with this kind of terminology. Racemic, you all know, equal amounts of RNS. Rectors and sinister, handedness. Okay, who is that? Ingold, Plug, and those guys. Yeah, can. Yes, those guys developed this. Both are present in the same crystal. That means space groups will have, you can define the arrangements by the space group. That will have inversion center, mirror planes, and glide planes. Conglomerate, you have 2 enantiomers, but in that mixture, you need to separate them as separate crystals. It's not in the same crystal. Like this, like ammonium, sodium, tartrate. Okay, I'll come to this after I finish this. The melting temperature, some characteristics. Melting temperature is lower for this racemic is lower than the melting point of the R and S crystals. Okay, each single crystal, if it is in conglomerate, each one should crystallize in a chiral space group. Okay, in solid solution, you have an equal amount of RNS. Let's go back to this ammonium, sodium, tartrate. Louis Pasteur, I think when he was 26 years, not 26, when he was working by himself, there's no postdoc or anybody. So he put it on the windowsill to crystallize. You see, this guy was working on wine. It's nice to work with wine in the lab. He was working because the winemakers, they had problem when they bottle it. It cakes out. Some crystals come out all the time. So they found out that it is tartarimectic. Tartarimectic is nothing but potassium. What is it? Antimony tartrate. Okay, tartarimectic. But they wanted to get rid of it. This bad thing when you drink, you also get crystals. That time they didn't know anything about crystal engineering. They don't want to. So, but he started looking at it, and he started crystallizing. Ammonium sodium tartrate. It's very similar to that, and then he started getting crystals. He should have. He didn't want to stop this. He looking at it under microscope. He found out that left hand and right hand, 2 different crystals. Even now, it's very difficult for us. And he was separating each other. He showed that one hand, rotate the, plane polarized light in one direction, the other one. So he showed dextro and here. That's right. So this is the first time people didn't believe it. People didn't believe it. Everywhere he has to go with his, he has to show that he has crystallized it, and he has to separate in front of everybody. He has to show that he's, successful. But the thing is, this happens only, well below 26 degrees. If it is above 26, he could have got only arsenic. It's very, very fortunate to have it. That's why he said in the field of observation, chance favors only to the prepared mind. Okay, this guy, he became professor when he was 32, and full professor when he was 32. He was paralyzed when he was 46, but he contributed a lot, just like Linus Pauling, right from chemistry and to crystallography here, to vaccination, fermentation, pasteurization, all kinds of things. This wonderful guy. Exactly. So now, after this, there is another guy who was doing the same thing in potassium chlorate. Again, this guy did this similar work. Potassium chloride, if you crystallize it, he got two-handed. It depends how you stir it. If you stir it in left to right or left to left, the other one. He got some crystals, and the potassium chloride is is a chiral crystal. It crystallized in chiral space group. He separated all these things and say that when you stir it in one direction, you get R, the other direction, yes, kind of thing. He published in Science in 90s. Anyway, it's very similar to that. Right now, whenever you talk about crystallization, we have to know about the phase diagram. This is the phase diagram of the few substance, say phenol. That's what they say. This information is, is very helpful in finding out the right conditions to crystallize. And as you see here, the phenol, and you have to know the temperature at which you can liquefy, and then you can get the crystals. Okay, so the atmosphere, it is plotted against pressure. The same thing when you have two component system. In this case, glucose and water. You just dissolve it and crystallize it, and you can produce this phase diagrams, and you get 1, 2, 3, 4, 5 different phases. Alpha, beta, and something monohydrate, dihydrate, all these things. And even in the two component system, it can produce so many different types of glucose crystals. And you see, if you're not very careful, you ended up only one. For us, it doesn't matter. But for others, it matters, actually, which form and everything. So these things are very important. And when so apart from phase diagram and everything, because that's the one we need to know the crystallization conditions and how the crystallization occurs. That's $1 million question. What's the mechanism and what's really happening? And people, have started working on that theoretically for the past 100 years. 100 years, what should have happened? There are a lot of theories. In fact, I remember for my PhD, I used one of the theories of Rees and Wilson for melting pot, for melting to phase transition, dependence on of crystal size on particle size on phase transition temperature. So something like that. So people at that time, I used 1923 work. So that means it's very well known for a long, long time. And also it's very complicated. It's very, very complicated. And there are so many things are available. Even if you change the conditions, if you change the compound, the theory will change. It's just like cancer. There's not like only one type of cancer and you can cure, and this is the mechanism. There are so many. Same thing with the crystallization. There are so many theories, so many ways. If you change a compound, the whole thing is different. But in all these things, three things, or maybe two things, are very, very common. What are the two things? Nucleus formation. Once a nucleus is formed, critical, so with the size, that's one stage. The second stage is once it is formed, the crystal growth. Only two. Let's, classify them into two, and then try to understand. The other things, involve maybe 3 or 4, and which comes first and everything. So let's not worry about this. Let's try to understand this in terms of thermodynamics. The plot that I've shown here. Let's imagine what is really happening in the case of crystallization. Case of crystallization, of course, as you mentioned, it depends on the conditions. So nucleus, first, the molecules should collide, just like any reaction, they should collide. When they collide, they form dimer, trimer, tetramer, they form a cluster. When they form it, they release some of the solvents, around it, and then they form a cluster. That's what is happening here. So, monomer, and then slowly, it started building the nucleus. It hasn't reached the critical size. So at that time, this is the delta G of surface energy, is the delta G of volume, the bulk. When it's really small, the surface energy, the surface area is large. So the surface energy is huge. So that will destabilize the formation of this kind of nucleus. That's why, because the surface energy is very high, delta G goes up. Although due to the formation of dimer and trimer, the delta G goes down. So once it's reached the critical mass, okay, we don't know how many. We just imagine. Even today, there's no proof of what is meant by nucleus. When about 3 years ago, somebody published a paper that I've seen, for silver nucleus. They have done using TEM, but so far, nobody has ever seen. It's all theories. Okay, so usually the delta G, the resultant delta G increases, like activation energy kind of thing. So delta G, there's an activation. At this stage, what happened? Where once it reached the critical radius, then it started growing. Then it started growing further. Because it's growing further in the size, then the delta G surface, the surface area, surface, what is it? The delta G of delta Gs, becomes lower and lower after it reaches the critical size, because it's the free energy of molecule, the free energy of the surface becomes less, free energy of the bulk, because delta H is increasing because of the formation of the bonds. Then it started going down, because they say that in step 1, step 2, step 3. So here at this stage, it's matured, and it started growing. When it started growing, then you can arrest it at any time. Arrest it and get new, nanocrystals. Because it started forming, it's stabilized, and you can stop it. So this is what is happening. So it's called a critical radius that it has to reach. So then you started getting it. So after that, it's not, it doesn't go back. Oh, but there will be so many nucleus formation inside, and then so many nucleus once formed, it started growing outside. So these are all happening in the supersaturation. Supersaturation conditions, in fact. So you can describe it in terms of equation. Once you know, the theoreticians will jump into it and give you interesting equations. So you can use this equation to calculate quite a lot of things, but many of them, we don't have experimental values. What is the size of the cluster? We don't know. You need to assume certain number. Same thing, volume occupied by the cluster, relative supersaturation. Boltzmann constant, we know, maybe interfacial energy you can calculate for the given radius. So, and also what is the critical radius, for the conversion of this nucleus into a stable growing, crystal. And we can do quite a lot of things, but just to show you that it is possible to calculate. but not possible to see anything, using any experimental techniques so far. But this is what happened. So once you started getting this nucleus, and they started growing into a big crystal. So at this stage, a lot of, we know about what kind of form it is going to, because the molecule interacts in one particular way. We know that this is going to be polymorph 1, polymorph 2. That will start dictating the nature of the crystal that you get at this stage. That's why the solvents and everything, the conditions are very important, for colliding and forming, dimer, oligomer, and then forming this cluster for the formation of, for the growth of crystals.
What does those green lines represent? The nucleus.
Oh yeah, see, this is actually, I took it for the nano, nano particles. So for nanoparticles, what they do, once after some time, you put in some surfactants. Okay, after 5 minutes, 10 minutes, because you want to arrest the growth. The surfactants will go and form a bond on the surface. So once it's formed, the growth is arrested. Actually, I took it out for the nanoparticle growth. That's why I'm sorry. It's nothing to do with crystallization.
And so
Just to explain to you.
what is the difference between nucleation and growth?
Nucleation is the formation of the critical size.
Then
Okay, once it is formed,
third stage.
and then many of those nucleus will combine together and start growing as a big. I'm coming to that. The next step. That is the next step. What you say is right. There is different types of mechanism. Even single one, can start growing from this region, but you can also have 2 or 3 clusters combined together, and then they will add one more, one each, and then start growing bigger and bigger.
That is also type of nucleation. Why we say differently as growth?
We started seeing it. Crystals, nucleus, we don't see them. Okay. Crystal, we see them. That's why we see it's growing. We can't say that its nucleus is growing. Of course it has to grow, but that's why we separated them. The one we see, the one we don't.
One is for microscopic reason, we use nucleation and so on.
You can say that. That's why I'm saying there are so many theories, so many ways, and this is the way we want to describe. Okay. For this, we have experimental evidences. Even now, for TM, SEM, and all, we can arrest the growth and get it. That's it. Okay. Thermodynamics. Still, now, only at this nucleus stage, polymorphs are decided. I just mentioned to you. Now, this one show you the energy profile for thermodynamics and kinetics of crystallization. This is one way. Okay. In this case, of course, delta G is plotted. For any crystal, there should be one form of the crystal that is thermodynamically stable. For any, there may be so many other things. That's a lowest energy, that has got the lowest energy. We say that it's thermodynamic. Yeah. And also it has to go through, when you have a solution, when you dissolve, let's say sucrose or whatever, glucose, and you want to get the crystals out by any means, evaporation, whatever, diffusion, and there are different ways of forming crystals. Okay, there's kinetic route, more than one route. It can, there's a activation energy. That activation energy is smaller than this one. Okay, that if it goes through this, you get thermodynamically stable compound. If it goes through this, you get kinetically stable crystal. Okay, if naturally you can expect this one to go through this and form. Okay, because activation. It's an example, but in actual reality, you may have different types of the activation process. For kinetics, there may not be anything for kinetic formation. There will be only one form. If you have one kinetic form, one thermodynamic form, yes, you can write. But Imagine if you have about 5 different polymorphic modifications that are possible. How do you visualize this energy level diagram? So you imagine, send a drone to the top of the hill. You start looking at it. So this is the hill, and this is a kind of lake. It has got water. Okay, water. And then you started seeing that around that you have a smaller lake. When water goes from one place to another, this is another place it can catch. Okay, the final one is the ground. Okay, there's no guarantee that water will reach the ground. If there is another way to store somewhere else on the way back, it will become another small lake. So like that, around the hill, you can have 5 different lakes and 5 different what is that, heights. If that be the case, you can allow the water to go into one side or the other side. It need not have to reach the ground. So that's what I meant. If you look at 3-dimensionally, if you have one more of this type of kinetic crystal that can be formed, it can be trapped into this. It depends which way the crystallization goes. So that's what is happening here. So this is a kinetic crystal, is nothing but a metastable crystal that is formed because of some favorable aggregation pattern in the molecule. So when its nucleation occurs, this is what is happening. Okay. So this is the form. This is why we say it's kinetic. Okay.
Sir, why this first nucleation occur means the first.
Why
this first nucleation will occur means? Is there any means change in the temperature or any influence?
Okay. Okay. Why when you mix it, why reaction occurs?
To reduce energy.
Exactly. The same thing. See, when one molecule or even few molecules, we don't know. We assume that the smallest one, you've got a glucose. Glucose will be surrounded by water molecules because it's hydration energy. Okay, when they go along with the all water molecules is going to move around, so they collide with each other. When they collide, they see some kind of attraction due to hydrogen bond. They release water in that in between them. Then they form, and then they started moving dimer. So like that, there will be Avogadro number of molecules will be moving around. So dimer, there are chances that it may break up, or it can form a trimer. Trimer will form a tetramer. So like that, it can also break up. Okay, that's what is happening if it doesn't reach the critical radius. Okay. So it forms and breaks.
And is there any requirement like rough surface or something?
No, it is not like that. All the molecules have certain volume, certain shape. Okay. It depends on what kind of molecules you put it in, right? You can have elongated or a flat, or it can be spherical. Depends on what kind of molecule you put into crystallize, and that's what you are going to get it. In the case of glucose, yeah, it's water. But in the case of other compound, organometallic compounds, you want to put in acetone or acetonitrile or something. And mechanism is going to be the same. Okay. So why it is formed? It's also breaking, right? Only when it reaches certain things, it starts again. So according to you, if you wish, okay, no, we don't want any formation of nucleus, there is no crystal. Right? So it will try to find some experimental conditions to, if there is a foreign entity there, then it go and stuck there, because of some superficial or whatever surface energy, they go and try to bond to them, and then started growing on that. That's why you see on the surface. Why do you see crystals growing on the inside of a vessel? It's because of that. It's rough. If it is rough, its surface is modified. If its surface is modified, then it will see that whether it is suitable. It's hydrophilic, hydrophobic, all kinds of things. So it's firmly in the sense supramolecularly bonded to it, just like a post-it kind of thing, they're stuck. So other molecules will come and collide with each other, and then some will attach to it, some will, yeah, that's what happens. So the kinetics versus thermodynamic dichotomy is not, polymorphism is encountered, but not for benzoic acid, urea, naphthalene, glucose. So you can draw the energy profiles, energy level diagram accordingly. So until recently, even aspirin was in this list. About 10, 12 years ago, they found a second form of aspirin. Okay, so that means we haven't found the suitable, maybe suitable experimental conditions to get it, or this may be the only stable or only form. We don't know. We don't know. This is an example. Maybe if you're interested, you start crystallizing benzoic acid and look for the second form. You'll be famous.
So when we talk about the polymorphism example, if a compound is having different polymorphic states, so will that the thermodynamic level, the product formation level will be different for them, or will the activation energy barriers will be different for them?
That's a very good question. It's a very good question. Finally, when you talk about it, we just forget about the kinetics. We look at only the stability, final thermodynamic stability. Yeah. So it's only how much efforts you put into get it. So at the end of the day,
Efforts means we are again seeing the kinetics.
yeah, at the end of the day, you don't care whether you put in 16 hours, to study, to write the exam. Finally, if you get, 96, which one they talk about? If you put in 16 hours, oh no, I'm the, so the other guy put in one, I should be the first one. No, they don't rank accordingly. Same thing like, the final one is thermodynamics. So that's the one that decides. Okay. Yeah. Okay. This one. Growth. Now we talk about the growth. What is happening? This is the solution, normal solution. This is the reaction zone, supersaturation. Okay, I showed you. So in one particular region, you started seeing supersaturation, where you see the crystal, just like queen bee. The crystal will be sitting there. All the small nucleus and small crystals will start bumping onto each other because it's got high concentration. So if it is low concentration, if it goes here, diffusion occurs, then it goes back to solution. Okay, because it started dissolving back. So it will be drawn here, so around this, and then when it's colliding with this, and then the surface energy will that will decide surface energy versus the bulk energy, delta G of surface and everything. So this is what happened. So it started growing just because you got quite a lot of nucleus coming in contact with the crystal. It started growing. Sometimes even small crystals. I'm going to talk about it in the next few slides. Okay, so this is what is happening. The rate controlling step for growth can be a diffusion of the species through the reaction zone or the solution. In other words, the rate of this surface reaction. So how much? So what happens if you have a crystal? You just disturb it, you just make it, so that the concentration becomes the same in all, then you don't grow anything. That's why you see whenever you grow big crystal, every now and then they replenish in the sense, okay, you are growing copper sulfate. After a few days, once a big crystal is formed, the concentration becomes very low. Then it started dissolving back. So you need to add more to keep it, so that allow more nucleus to form, more small crystals to form, and that will contribute to the growth of the big crystal. All right. Right. I mean, well, I can move. So when it grows, there are so many models again. These models you can experimentally verify. Okay, very easily. There are so many. I'm going to show you only a couple of models. simple growth models. So this is Terence Lodge, whatever, this is for the crystal growth. Let's take a look at this. When the crystal, started growing, okay, I mean, well, you can't ask them to, I mean, there's no way we can force them to grow, very on the planar surfaces, on equal thing, but one side started growing, the other side is not. Slowly, it started growing as a cube, there's a kink site, and this is the one highly reactive surface and, energy wise. And then energy wise, this is very active. So it will allow the formation, growth of the things in this region. And then that forms some kind of steps. You always get a step and a ledge here. So more and more nucleus will collide and start forming, and they deposit, and then crystals start growing in one direction. So, if you see, some of the surface of the crystal using AIFM technique, you can clearly see the formation of this, the steps like growth. Okay, this kind of thing you will see. The second one is, it is screw dislocation. Its name is screw dislocation. It started growing this way. And again, they have their own mechanism, the way it grows like that. Sometimes it gets twisted. You start getting twinning, two crystals stuck together, because on the free energy of the surface is conducive for the growth of some other crystal. Two crystals will come in contact and they started growing. Okay, these two single crystals completely, they have different planes started growing here. So what you see here, when you take a crystal and when you look at it, even on the microscope, they have beautiful surfaces. Reflection is perfect. But if you take a look at the AIFM technique, horrible looking. It's not planar surfaces at all. Just like looking at our, there's a shiny, cheek. I mean, just using, thing, it looks good. But if you look at using SEM or something,
Yes.
or the same thing here. It looks really beautiful here. But you can start seeing the kind of mechanism, what kind of growth is happening. Once you have small crystal, you have all the experimental evidences. What we say is dislocation. Actually, it is not dislocation. It's mechanism of growth. It's a mechanism of growth. We don't allow them to grow. We just take it out. That's it. And then even if you polish, you will have this kind of thing. Only AIFM, I'm not sure. Using AIFM, you can determine. So AIFM can determine whether it is a cleanly polished surface or a flat surface, and that will tell you. Even some crystals may be knocked off when you try to polish them on the surface. So there are a lot of such things, grain boundary, epitaxial growth, and crystal twinning. People started saying this is defects on the surface. Even in the bulk, you have defects. Okay, I'm not going to talk about it. This is on the surface. Sometimes it helps. All the defects are, once upon a time we always think that defects are bad, but defects are good. Even among us, it's better to have defects. Well, let's move on. Yeah.
Is there any reason behind the crystal twinning?
Oh, I mean, the reason is, well, when crystals started growing, one particular, for various reasons, one particular plane or surfaces matches exactly. It depends on the matching of different Miller planes. Energetically, it should favor. Not everything will form, this kind of twin crystal. Certain high symmetry, one will form. Only high symmetry. Low symmetry, you don't see twinning. Okay. Because all the planes are very similar. Energetically, they are the same. They have similar energy. Because of that, this is the problem. It get confused. It started growing, thinking that this is one plane. Actually, it is one bar, one plane kind of thing. It's going in different direction. Although symmetry-wise, it's the same.
Sometimes we see that even the pure elements also exist in such type of forms.
Pure elements will crystallize with all kinds of twinning.
Yes.
Because it's spherical, right? You're trying to take the spheres and try to,
Symmetrical.
yeah, highly symmetrical. Highly symmetrical.
Like I think molybdenum or but tungsten crystal, when it is taken out from Earth's crust, as cubic like meaning is fine, but cubic can be out for the circular, fully circular, and that is why they are showing to it. Why are you saying that?
I think for that other factors like many things are mixed there in the earth crust. When they have come out of earth crust, they are not in their pure form. Many other defects and impurities are mixed. So I think it will they are the reason behind that form, which means
But they are very precisely cubical when we see that. But really cubical, lot of cubical things are very much together. We see that.
Many times, this kind of twinning, you can very easily identify using with naked eyes or under microscope. But there are, crystals you can't make out unless you put it on the diffractometer and start getting the diffraction pattern.
Yeah.
Okay, that's immediately you see you can't solve the structure because get confused. Okay, now this one may create some interesting discussion, I hope. Oswald ripening. Oswald ripening is the tendency of large crystals to grow at the expense of smaller crystals. Okay, that means whenever you have a big crystal, when a small crystal is also growing, it will dissolve, the other one will start growing. This is like bigger fish eating smaller fish eating even smaller fish. Okay, first you may think that, okay, if you're a socialist, you can always say that, oh yes, this is what is happening. Rich people are eating poor people. Okay, but actually, if you see, I'm going to explain to you. It is in the case. I mean, I'm not talking about that socialist, attitude, but here it is natural. Even here, big fish eating small, because that's, it's looking at it. It's food. You don't see that differently. Okay, you can't, even if you cannot give chapati and other things. I mean, they won't eat. It's a natural thing. Only human being can eat chapati. Okay, not eating fish, but not the other way. So that's what is happening. Okay, coming back to this. Now, why this is happening? Smaller crystals nucleate easily, grow kinetically stable. Okay, so what is really happening? Take a look at the the surface area. Take a look at the bulk. The surface area, the ratio of the surface area, surface area to the volume. If you take a look at it, for big crystal, it is small. The surface area is small, volume is big. Okay, so it is not the surface energy that's going to interfere anything, because you already have lots of delta H in the bulk. So so what happens? This is more stable. On the other hand, if you take a look at the smaller crystals have smaller volume, greater surface area. Because of that, the energy wise, it's easy to go back to solution, or just transfer the molecules to the bigger crystal. It's thermodynamics, nothing else is thermodynamics. So thermodynamically, this kind of growth is favored. I mean, I don't want to get into the arguments of rich people eating this. This is what is happening for fish also. That is natural. Okay, that's why I'm showing this. So growth of large crystals are thermodynamically favored. Okay, so that's what it's called, Oswald ripening. Big crystals getting bigger. That's natural. Don't compare with anything. Right. Let's move on. I don't know why I'm not able to do it. Yes. In the morning, someone asked the shape and morphology. Now, here the answer. We don't call it shape. Instead, we say habit. Habit. Okay. Let's see. Let's take a look at this pair and this pair. This pair has the same morphology, same Miller plane. Okay. Only thing, this is bit, got lot of parota. He's doing a lot of exercise. The same morphology, but different habits. This one, they have the same habit, but different morphologies. Now, with that, let me try to explain here. Crystal morphology refers to phases of the crystal and interfacial angle. Because that is the basic thing, because the internal symmetry reflected onto the external morphology. So same Miller, planes, the angle, interfacial angle, although the shapes are or the habits are different. So in the case of habit, it's a more like qualitative descriptor and describe the shape. Okay, this is a shape. There can only be three. Cube or prism, needle or plate. Platey. You're describing plate. We say habit. Okay. So morphology, crystallographically, they are similar. They are the same. Okay, they are the same. The same different shapes. But you can recognize very easily they belong to each other. On the other hand, these two look, it's all tall and lean, but these two are completely different, morphologically different.
In the perspective example, are they both having the same crystallographic planes? Angle is fine, we can see that same.
Plane also.
But in second, we can see that plane seems same, but
here it is cut here.
And in first, we can see that angle is.
No. I mean, see, this is dramatically it is drawn. What I meant was, if it is needle, needle, two different needles. I can draw it a different way, two different types of needles, just to show that it has got two different morphologies. But the shape or the habit, we say that it's needle-like. Okay. Maybe the way it is drawn is maybe confusing, but needle is a needle anyway, the long one. Okay, I should produce a thinner one, not exactly. See, the way it is drawn may be something different. The size on other two sides, I have to cut it into small. Yeah, just to show that it is not the same, but looks like, yes, I agree. But actually, it's only the habit, the shape we are talking about, similar shape, but not similar morphologies. Because of, maybe you can put the angle here, maybe more than 90, here is 90. All right. I say 91 is 90. Okay, it's drawn wrongly, maybe. Okay. All right, let's move on. Okay, crystal morphology. Okay, let's go back to crystal morphology. I said the morphology, the internal, if you look at the morphology of the crystals, if you crystallize, some high symmetry one is cubic. Cubic can show different, morphologies like this. Okay, but you have to correlate. You should know how to correlate it. How you can correlate is cube. You started chopping the corners progressively, more and more. Take a blade and cut it. So if you cut, first time you get something like this. You get more. You get different one, third one, fourth one. So cube becomes octahedron. So in between, number 4 is corner truncated octahedron. Okay, this corner truncated. Third is cube octahedron, corner truncated cube. So you see the relationship. Many times what happened, depending on the experimental conditions, you may get either octahedron or cubic. Again, coming back to the real example, potassium chlorate, KClO3. Based on the conditions, you can grow an octahedral shape or a cubic shape. Actually, we had given this for crystal engineering challenge to undergraduate, high school students several years ago. To say you have to grow only cube like KClO3 or octahedron like, they're able to grow it. So they have to find the right conditions, and which has been described in the literature. Okay, so it's not that you cannot. No, it is possible. You see the correlation. So that is the internal symmetry. Here also, if you look at the symmetry, they're all reflected onto this. And if you have highly symmetrical compound, you should also be able to, I mean, these are all planes. Okay, if you have octahedron, you have cubic, you can identify the planes, Miller planes. We all know, we have studied, and you can do it. Crystal morphology engineering. This is what is called crystal morphology engineering. It's very, very important in pharma industries, in the process of better handling processability. I mentioned to you at the beginning, flowability, compactability, all these things. Sometimes, this is what they call tabletability. If you're able to make tablet, the other one you cannot, tabletability, flowability. These things are very, very important for pharma industries for processing. Okay. And also maybe for other industries, this is important. I'm going to show you how you can control the morphology. The next one. Yep. Okay. Tailor-made inhibitors. I'm going to show one example how you can control chemically. It's not blindly you just trying to do something. Okay. This is benzamide you want to grow. This is the structure that is shown here with hydrogen bonded pattern. Forget about this. So it grows something like this one-dimensional tape. It started forming. And once this is formed, the second layer can be added to the front. So that will be stabilized by pi-pi interaction, right? So they may be apart by 3.5 to 4 angstrom. Can very nicely you can pack it. But if it started growing this way, because all hydrogen bonds easy to grow in this direction, you started getting what do you call plate kind of thing. It started growing this way, it started growing this way, you get nothing but plates. This is the normal morphology of benzamide. When you try to do that, you get platy kind of crystals. So now, when you started growing crystals, what do you do? Maybe when you started seeing very small crystals started growing after nucleation. So you just add additive. This is benz, what is it? This is function. What is it? Benzoic acid. Yeah, benzoic acid you add. If you add benzoic acid, what will happen? Benzoic acid. This is benzoic acid. This is benzamide. Now, yeah, you started adding benzoic acid here. Benzoic acid will also get into here very nicely. So when benzoic acid is added to this, so the further addition of amide becomes a problem. Once this is added to this chain, the second one comes, it started repelling. Okay, according to this, they say that it stops. So it stops on 4 sides, and then these crystals start growing this way. So you get a different rod-like thing. That's what you are getting just by adding an additive. So this is very common when you're trying to grow crystals. You add a small amount of the additive, and then you start getting a different morphology altogether. This is one. There are so many examples. Maybe you will see. One can also help industry people to grow to get the size or the habit of the crystal they want, by doing this kind of additive.
Yesterday, we were also discussing some structures here in which there were 2 hydrogen bondings from the same acceptor atom center. Why the oxygens are repelling here now?
Why oxygens are?
Why after using that benzoic acid, that is fine that one more hydrogen isn't present here for further nucleation. Now, why they are repelling? Why can't they form a hydrogen?
No, because if it but it can't form bifurcated. No, it cannot form. Then the whole thing, okay. If it starts right from the beginning, if you get nothing, you cannot get one crystal, one, bifurcated one, and then the rest will be normal. That is not possible thermodynamically and kinetically.
This is
if you get the whole thing, yeah.
We have said here that this will repel each other, so we will just get a plate type thing. This is not going to happen in normal general conditions. Either we need to have special conditions that only this plate type formation happens and no other bifurcation occur.
No, if bifurcation occurs, it happens to the whole bulk, not to just, it can happen on the surface. On the surface, if you look at it, you will have benzoic acid. That's it, it's terminated. Okay. All right, the whole, thing, it is terminated with that. That's what happened. If you see, your diamond or any extended solid, take a look at it. See, if you look at the surface, you see all carbon will be there without, the valency fulfilled. No, it will be completed by other hydrogen, chlorine, or so many gases that will bond to it. The surface, you can modify the surface, but you can't, you can't say that I don't want anything on the surface. The same thing with zinc sulfide, same thing with any extended solid on the surface. The valency is not fulfilled. The bulk, yes, not on the surface. That's why they do a lot of surface chemistry based, on the surface, modify it and then do it, and they stick onto that and doing all this. For the same reason, here.
My doubt is that what are the special conditions or the measures we should make to just to get plate type thing and to avoid bifurcation in whole bulk?
Avoid bifurcation.
To avoid bifurcation in whole bulk phenomena.
Yeah, so this doesn't form bifurcation. That's what I'm saying. This doesn't form. So once it is bonded, it is terminated. The growth is terminated. Once the growth is terminated, some other place it has to start. Okay. Yeah. On the other surface, things will start growing. Okay. The unit cell length. Okay. A little bit of crystallography, but not much. But we know the basics, like cell data, ABC, alpha, beta, gamma. That one we know. We always take a look at it. We know that based on the angles, we can say whether it's orthorhombic, triclinic, monoclinic, and all these things. We are all familiar with that. Okay. But usually it's not the angle, because the angles are 90, it's orthorhombic. It's because of the symmetry. Okay, the symmetry enforces the angle. Okay, you need to remember, but never mind. So usually when we take a look at the ABC, okay, there's some number, right? Now we know crystal engineering. Now take a look. If it is something like this, 9.2, 9.3, 11.2, it's almost equal. If you have the cell lengths approximately equal, you will get equidimensional crystal. Okay. You can grow crystal with more or less equal dimensions. Okay. If you have something like what you say, one of the units of length is much smaller than the other two. One of the things is much smaller than the other two. Like this, it starts growing as needles. If two are smaller, one is bigger, this side will be look like a plate. Okay. If one of the unit cell is much larger than the other two, it grows as a plate. So when you try to grow crystals, if you know the cell dimensions, you can expect what kind of habit or shape you can get.
Plate and ribbon, both are same.
Ribbon, ribbon means it's flexible.
Oh, plate is not flexible.
Ribbon, you can say, usually molecular structures, ribbon is say. It looks like ribbon, but when it comes to crystals, you don't say ribbon like, we always say plating, needles, or prism like, or cubic.
I have read one paper. They mentioned that they found two types of crystal. One is needle, one is ribbon.
Ribbon may be like, they cleaved and they started getting something like, tape like this. They're able to do it. I don't know. You should ask those guys.
Excuse me, sir. I'm again disturbing you that
No, no, not at all.
the line, when one of the side is very small,
Hmm.
other two are big.
Hmm.
You said that should be middle type formation.
Yeah.
If you practically think that shouldn't be sheet,
Okay. Okay. Let me try to explain to you. See, this, I mean, if it is really one side is longer, what happened? You will know later, okay? Because I didn't explain a lot of things. In the reciprocal space, they're all closely packed. The closely packed, that side will be smaller, that's shorter. Okay, that's the reason. If it is longer, that means that side is shorter.
in reciprocal, it is short.
That's why. Okay, you have to know that. Okay, so that's what is happening.
At reciprocal, that is.
Okay. Let's move on. So this is the like rule of thumb. I mean, of course, under different conditions, you can get different shapes. Okay, I mean that's what our students are doing by modifying the crystal conditions, and sometimes you get nothing but cubic type of thing, but really want needle type or large plates type of thing for bending, for mechanical bending and photo bending. And some students are able to get it by changing the experimental conditions. They get really long needles, okay, or tape, like what you say, long rod like thing, long rods. So they're able to bend it. So it is possible. And not that I mean, but this normally under normal conditions, it's not growing something like this. Okay, this is the summary. I think it's almost time.
Yeah.
Okay, so I'm not going to summarize and these things for you to read, and all the things whatever we taught. I just put it in for you to go through at the end, so it's easy to understand. What is important is this, because we learn about crystallization, we know what you are supposed to do. Life is nothing but a crystallization process. You boil your ego, right? Dilute your sorrows, evaporate your worries, filter your mistakes, purify your thoughts, crystallize your happiness. All right. With that, we'll stop today's lecture and we will start tomorrow.